Okay, so I started the recording. Now, as you can see, the title of the paper, Tools for the Performance Optimization of a Single Photon Quantum Key Distribution. So here we are going to talk about performance optimize, how we can optimize the performance of single photon key quantum distribution. So in today's information-driven society, ensuring secure communication has become increasingly important. Privacy communication is essential to safeguard sensitive data, and quantum key distribution presents a promising approach to this challenge. So, what is the key concept of QKD? We'll look into it. QKD exploits the quantum properties of light, such as superposition entanglement, to ensure secure exchange of cryptographic keys. This security of QKD lies on a fundamental principle of quantum mechanics, like no cloning theory. So basically, the essence of no cloning theorem is like we can't copy another state. Like if there is a psi, we can't produce a two psis. So that is a no cloning theorem. So the second is QKD allows two parties to exchange a cryptographic key that is theoretically immune to interception by eavesdropper due to the disturbance caused by measurement in quantum mechanics. So when you will try to perceive that signal which Elisa sent. But what he will do is he will change the signal unknowingly because it will disturb the signal. So the end signal which is received by Bob would not be the same. So here quantum key, just a second. Okay. So here quantum key distribution. So here I have provided the image of like BB84. This is basic setup of BB84, which you can see. So the challenges in quantum key distribution. Despite the promising potential of QKD, several challenges need to be overcome. One of the most significant challenges is difficulty of fabricating high quality quantum light sources that can reliably generate single photon states. So what like previously was done was like researchers use this weak coherent source of light, which essentially mimics the single photon source, but sometimes it transmits multiple photons, which so after transmit that multiple photon, you can easily perceive that signal, and because there are multiple photon source, so if you can get one of them, he can interpret what the signal is, so that is not reliable in real life scenario. But this author has used a second setup, which is quite technologically advanced. So this setup has a G20 of 0.082, so that is quite low, and which is essentially a single photon source. But what are the major challenges? So if for a quantum light source, secure QKD requires a reliable single photon or integral photon sources. Producing these sources with required properties such as a photon indistinguishability and stability remains a major challenge. Okay, as I've discussed. Practical implementation of QKD systems suffer from imperfection in quantum light source, leading to suboptimal performances. Hmm. So now here, what he has used, quantum light source. So what would be a quantum light source? Entangled photon pairs. These pairs of photons are produced in a quantum process that links their properties, such as polarization or phases, even over a long distance. The entanglement ensures that the measurement of one photon's property will instantly affect the other. And now the second is single photon source. A single photon source can emit individual photon in a controlled manner. These sources are used in a QKD for securely encoding cryptographic keys. So we are provided the image of quantum light source. You can see here. This is a basic setup. Well, it will trigger, and this quantum light source, the emitter will emit the photon, and it will send out single photon source pulses. So next we add to is temporal filtering, which is the main topic, main discussion in this paper. So what is temporal filtering? It plays a crucial role in enhancing the performance of QKD system. It refers to selecting photons with a specific temporal shape or duration that matches the desired properties of the system. So what are the benefits of temporal filtering. So improved signal to noise ratio. So what it does is like it removes the noise. So essentially, what left is uh, signals. So the efficiency of signal is improved. So improving the signal to noise ratio. And the second one is tolerance to losses. Since all system experience some level of photon loss, temporal filtering allows QPD system to operate effectively even under suboptimal conditions, such as during a long distance transmission. Okay, so I provided diagram of temporal filtering. So this temporal filtering, you can see we have neglected this noise region, and then they've only selected this signal region when there is signal. So improving SNR ratio. So now next we move to experimental setup. So the paper's research focus on optimization of QPD system by analyzing the temporal characteristic of single photon source. The study emphasizes the use of realistic quantum light source as a most theoretical studies assume idealized sources that are not always practically achievable. But now here authors try to achieve this practically. They have used a setup in which the G20 is very low, mimicking or essentially not mimicking, but producing a single photon source. So the single photon source, the experiment uses triggered single photon sources and entangled photon pairs, which are core of the many QPD systems. The receiver module, a module designed for a four-state polarization coding, is integrated into the system which decode the key securely. So this is the experimental setup we can see here. So here light is passed here, which is a polarizer, which will set what you say uh, coordinate system, which will set the basically this photon coordinate system. And here is a beam splitter. So this is basic setup of they've used for BB84. So now here we come to the conclusion. This work explores the temporal filtering of a signal photon pulses to optimize the performance of QPD system, especially in realistic scenarios. By improving the signal to noise ratio and the system's tolerance to losses, this research contributes to the development of more practical and efficient QPD system. These findings are crucial for ensuring the future of secure quantum communications based system based on quantum light sources. So here I stop completing the introduction part of this paper. We'll stop here.
My name is Pranshi Chorsia. I'm second year MSc student. Today here I will talk about KKD testbed. The quantum key distribution testbed was designed to implement the secure communication using a semiconductor quantum dot single photon source. Here we are using quantum dot semiconductor quantum dot for single photon source. Okay. This device emits the single photon at an emission wavelength of 18 nanometer with a low multiphoton emission probability reflect in an anti-bunching of G20 is equal to itna. Means that G20 is here we can see that G20 value of G20 is very small. Means our source is very good for getting a single photon source. Okay. In the following, we investigate performance of a QKD testbed, assuming an implementation of BB84 protocol by analyzing the achievable QBER single photon purity and the secret key rate. What is the QBR? QBR is the mismatch in the bit when bases are same in BB84. When the bases are same, what is the mismatch in the what is the mismatch in the bit? That error we talk about QBER. Okay. Now in second figure two, we will talk about the setup. Here we can see that this quantum dot single photon source will emit a photon, will emit pulse, which will not be polarized. After passing this polarizer, that will be polarized, and after passing by this wave plate, wave plate, it will orientate in some direction, like horizontal, vertical, and diagonal, and anti-diagonal. This wave half wave plate will rotate the polarized light in by 2 theta. Okay, by optimizing in best way, we will get horizontal, vertical, diagonal, and anti-diagonal in as an input in beam splitter. Okay. Next is when this light beam splitter will split it in two direction, which will have a 50-50 probability, whether the at pulse will go in D or A channel, and whether maybe the ad that pulse can go in H and V channel. It has a 50-50 probability. Okay, first and here, first we investigate the limit our introduced to the total QBR expected in full implementation of QAD. For this process, we record the photon arrival time distribution at the four detection channel of Bob for four possible input polarizer of a single photon source. Now, here what we are saying that, okay, by this figure we can understand what we want to say. Like we are saying that if this input light here, if the input light is horizontal, then that horizontal pulse can go either in this channel or either in this channel. If that horizontal polarized light goes in this channel, then there will be 100% probability that this channel H will detect that pulse with the 100% probability, and there will be no pulse detected by this vertical channel. And if the light will go in this DA channel, then it will rotate. If that was first, we were saying that that is horizontal. It will rotate that pulse as a diagonal or anti-diagonal, and then we will get 50 probability that light will either go in D or A. That's why here we are getting D and A. Similarly for V, that V will go. Either can it can split in. It can go in this channel or it can go in this channel. If the vertical light go in this channel, then the V channel will detect the pulse. That's why we are getting here the peak, and here we are not getting the peak. Similarly, if that V polarized light means V light, V pulse, if go in this channel, then we will have a 50-50 probability that either it will go in D channel or A channel here. Similarly for D and A, if D, let's talk about D. If D pulse will go as an input in this beam splitter, if beam splitter if that pulse will go in this channel D or A, there will be 100% probability that either that will detect by D or that will detect by A. That's why here we are getting D, and A is 0, because our input is D, and that's why, and D channel we are getting 100% probability. If that light will go in this way, because that is a 50% probability, then there will be a splitting. There will be a splitting 50% probability that either it will detect by the H or V. Similarly for A. Okay. Here one more diagram is there. Here it is what it is showing. But here we can see that there is a blue peak, and there is a one brown peak. What is blue peak? Blue peak is here, that horizontal light is coming as an input. Then all light should detect by H here, when the light is following this path. But it does not happen because there are some mismatch in the optical, and there is some mismatch in this beam splitter. Okay. So if let's say 100 pulse are going in this direction as a H input, then 92 will detect by this H, but 2 will detect by this V. That's why we are getting as a brown here brown for two detection, and this blue is detection for 98. Here we are getting the same peak because what is happening, we are normalizing it by the detection count in the, by detection count on this channel. Okay. Means here we are getting two, here we were getting two, we were normalized by it, we were normalized that peak by two, and here we were getting 98 signal. That's why we are normalizing it by the 98. That's why both the peaks are similar. And here we are also getting very small, we can see here we are getting very small dark count also. Same for this and this and this. Now, next we'll talk about the quantum bit error bob. Quantum bit error bob means how much error we are getting. First, p q into p signal by p click. P click means total detection count, total count by detector. Okay, whether it is p signal or whether it is p dark. Q multiplied by p signal. Let's say p signal is 100, means 100 signal it sent by this quantum dot, and it is going in this direction, beam h and v. Let's say 100. We are Let's assume that 100 pulse are going in this direction, h and v channel. Then if this is if that 100 pulse are at H polarized light, then all the light should go in H, but it does not happen. Like very few of very few of pulse will go in the V. That Q here, that Q is the fraction that will go in V multiplied by P signal total divided by P click, means P signal plus P dark. Here P dark by P click. P click means this will also contribute in the this will also contribute for in cube error, which will be dp pd p dark count divided by p click. Okay, now I'm handing over it to Aryan Prakash. Stop share.
So thanks, Priyanshu. And hi everyone, my name is Aryan Prakash and my roll number is 23N0297. And till now, what we have discussed is that is the introduction and motivation of the experiment, like why are we doing it? And Priyanshu also discussed about the experimental setup of the experiment and what do we actually expect when we don't use any specific technique, what do we expect to get? Okay. So the point that we'll be looking at now is how can we optimize the performance using some specific technique. And the central idea of this paper, the central technique that's used here is temporal filtering. Like what would happen if we perform temporal filtering in a QKD system, and what are the things that would improve and what are the trade-offs that we need to look at. So first look at what were the problems. So in, as you can see, in any QKD system, the imperfections of the system, such as the detector noise, the photon arrival time, all of these can degrade the quality of key that's being generated. So one way to improve the performance, particularly in single photon QKD, is to use temporal filtering. And let's look at what exactly is temporal filtering. So temporal filtering refers to the process of restricting the time window during which the photon detection events are considered valid. Now, this allows the system to discard photons that are detected outside a designated time window. What this means exactly is that when we wish our detector to be on exactly, like when the photon is being fired from the source, after how much time we want our detector to be on, so that we just cancel out the unwanted noise that we get in between, like the dark counts from the detector, and what would be the impact of this technique on all the other things. So in the context of the paper, The authors show how the technique optimizes the QKD system's performance by reducing the quantum bit error ratio and the secure key rate as well. And also it means shown that how G20 is impacted by this. So first of all, temporal filtering has a direct impact on signal to noise ratio, because if you look at this graph, if you look at this curve, you can see how uh, this temporal filtering actually works. Like if we pick a time like t is equal to 0 and we only switch on our detectors between the in the width of 2.5 nanoseconds around this central time 0, so we would only get the signals in this region and will not get the dark count signals anyways. So if we do this, what will happen exactly is that it will have an impact on signal to noise ratio, because now by limiting the photon detection events to a small window, we have decreased the dark counts. We have decreased the noise, which were typically random. So this results in a clearer signal, and the noise is quite less. So if we reduce the acceptance time window to that level, the signal to noise ratio will be better. So some useful photon detection events might also be discarded if we actually take it too small. But if we take it in a good healthy range, then we can actually have a positive impact on our signal to noise ratio. And the second thing is that and also if we do that, if we increase the delta t, then we'll have an impact on QBER as well. So our whole point will be to find the optimal trade-off between reducing the QBER and the shifted key fraction, and hence thereby maximizing the secure key rate. So now let's first look at what is the quantum bit error ratio. And as you know, QBER is a crucial parameter in quantum QKD. So that measures the fraction of errors in the shifted key, which arises from the imperfections in detection process or channel noise. So thus, QBER provides us with an idea like that how much noise and error are we expecting from our system. So, for an example, let's consider that the setup that we saw previously. In that setup, if we send only we look at only the H channel, then the QBR will be the erroneous detections that happened on the H channels, like the V photons that actually landed on the H fan, like the H photons that actually landed on the V channel, which is NV, and NH is the actual H photons which landed on the H channel. So the error here is NV. The erroneous bits are NV, and NH plus NV are the total number of bits. So what QBAR is giving us here is the error contribution, is the error, how much is the ratio of error with the actual signal. So thus, QBR is actually calculated by considering all photon events that are detected within the time window delta t and which are centered around TC. For example, in this curve, as you can see, the TC is 0 and the delta t is 2.5 nanoseconds. So as temporal filtering is applied, the system reduces noise, especially from dark clouds, which do not correspond to real photon events anyways, because these happen when you don't get these don't happen because of any signal or because of the optical imperfections of your system. These happen just because of some random fluctuations around. So by narrowing the time window, the system actually focuses on the signal photons. So as you can see here, the system is only focusing on the time when the actual signal is coming. So it is focusing on the signal photons, and hence, as you'd expect, as as small you go, the QBER will get smaller. Like the ratio or error ratio will get smaller, as you can see in this curve as well. Like when the delta t is quite large, the QBER is quite large as well, because of high dark counts. So when we try to when we reduce it, then the dark counts reduce, and hence the error ratio reduces as well. And this reduces up to a specific point, after which it kind of saturates, and it's because then you are inside this signal channel, like inside the part of the whole this whole curve, when there is only signal. So after this, there are no additional detector counts that uh, you'll expect to have. So uh, hence it will go to a plateau. And also let's discuss what would happen to the shifted key fraction. So the shifted key fraction that is shown in this curve as dotted line. So the shifted key fraction is actually the fraction of the shifted keys that you actually get divided by the total number of keys, the total number of keys, bits or signals, whatever you say it, you receive. So the fraction will be whenever you will take a delta t which is bigger than the size of the signal, then all of the signal bits are actually inside it. So in all of that region, you it will be approx one only. But when you come to such a delta t that you are cutting the signal actually, so the bits that you are actually getting by the bits that were sent are now decreasing very rapidly, as you can see here. So this is the kind of behavior that fraction will shifted key fraction will show us when we reduce delta t. So what is actually happening here then? In the plot, you can see that as the time window decreases, QBER decreases, but at the cost of reduction in shifted key fraction. So even if we reduce the error, at the end we are getting actually a smaller number of keys that we actually send. So this from this you can see that there is a trade-off between actually how many bits you see and how many errors you receive. Like if you try to minimize the errors, you might end up minimizing the information that you're actually receiving. So we will have to find an optimal delta t and optimal width when the trade-off between the QBER and fraction is what we aspire of, like is what we desire. Again, trade-offs and temporal filtering is what we'll look at now. So the first trade-off is the signal to noise ratio and shifted key fraction. So as we have seen in the previous graph, when we reduce the acceptance time window, we improve the signal to noise ratio because we have removed the dark counts and hence reduced the QBER. However, the cost of this is the loss of information, like the loss of valid photon detections, which mean that we have fewer shift bits for the final key. And the shifted key fraction, as I've discussed earlier, is defined as the fraction of valid photon detection events to the that contribute to the final key. And as it will shrink, the some valid photon signals will be discarded as well. So this paper discusses that the optimal QKD performance is achieved when we balance both of them, like when we balance low QBER and high shifted key fraction. So this is the main overview of things, and we will also look at now that when we do temporal filtering, what will be the impact of it on other things, like uh, on other things that can have an impact on our QKD performance. So first, look at uh, what would happen to the statistics of the quantum light source that we are sending. Actually, what we are sending is a single photon source with a very low multi-photon probability. So as you can think of it, the multi-photon probability will be actually directly proportional to G20. Like the smaller the G20 will be, the smaller the chances are that will be multi-photons in one pulse. So uh, this is one formula that's come up that's been derived somewhere else. So where PM is shown to have a upper bound on half mu square G20, where mu is the mean photon number per pulse. So reducing G20 will help us minimize the multi-photon events. And as we have seen many times that if we minimize the multi-photon events, that actually reduces our risks of photon number splitting attacks. Like if there are lesser photons, then the split will be lesser. But there will be not enough chance to split it. So that will lead to a more secure QKD protocol. So we will see further on that how temporal filtering actually reduces G20 and hence reduces the multiphoton probability. So let's see here that temporal filtering of photon detection events actually improves anti-bunching and security. As you can see in the curve that's shown here, that if we take the delta t as 12.5, like we're never switching off our detector, then the correlation that we are getting is actually higher. And this is because whenever we are getting multi-photons, then there is actually a delay between the two photons that are released at the same time. Like they're not exactly released at the same time in a multi-photon pulse. There is exactly a delay between them. So if we try to reduce the size of delta t, then there will be a point when the second photon that was actually released will come later than delta t, like when the detector is actually off. So that will actually decrease the multi-photon probability, that the pulses that have multi-photons that reach our detector. So this can be seen in the curve as well. Like as we try to reduce delta t, we can see that the G2 zero value is actually decreasing as we reduce delta t, and at a point where we have picked it to be 2.5 nanosecond, it has actually gone to be the least of the three cases that we have taken here. So to take the full advantage of temporal filtering in G20, also not only so, like this is the point that we have highlighted. There's also a good point that the authors have highlighted in the paper, is that we can we can do active gating or monitoring of G20 at ELISA's end. And how that would be beneficial for us is like, see, we switch on our detector for delta t time only. But what if there is the multi-photon pulse that was arriving, the other photon is arriving at a later time. So if Eve comes in between and gets to the line, that gets the channel where that photon is being shared, and the channel gets compromised, there will be no way for us to know because the detector is off. So what would be better is to have an active gate here, which will just block for further photons when the detector is off. So there will be no photons roaming around when the detector is off, or hence it will decrease the chance of Eve to intercept. So this is also a very good point that's been highlighted in the paper. And now let's look at how it will impact our temporal filtering will impact our security key rate, secure key rate. So secure key rate is also a very important performance metric for any QKD protocol or any QKD experiment that we perform. So what is it? The secure key rate means that for every pulse, how many bits do you actually receive? And this will actually depend on both the QBER and the shifted key fraction. So as you can see, the formula of S, which depends on delta T and TC both, is P click by 2 times beta tau E Fe He, where beta is the probability of single photons arriving at the detector, which would be 1 minus PM, which is the multiphoton probability. So, and tau E is here to incorporate the attacks of E, like to compress what would be the attacks. So, and Fe and Fe is the He is wait. So here Fe is the error correction efficiency that we can have. Like if we have a perfect error correction, then Fe will be 1, and other than that it will be greater than 1, and He is the Shannon entropy. So what is happening in this formula is, this is if there are more errors, then this will reduce the whole S, and because of which the secure key rate will be quite less. Like in whole pulse, uh, there will be less number of photons that can be actually called secure. So we will look at how this S will vary when we change our delta T and TC. And this will vary because delta T and TC change QBER and QBER and shifted key fraction. So further we'll see, we're going to analyze this whole formula and do some simulations about it. But this is what we expect from our simulations. And the setup of simulations is that we have a 2D plane where one axis is delta T and one axis is TC. And in that we are having a heat map of S, that is the secure key rate, and we are trying to find out what is the most optimal position that we should have to optimize, like to have the best S. And for example, there we'll get something like this, that there is a point where it will be maximum. So we'll try to have that in our experiment so that we can have most secure communication possible. So now, also the temporal filtering has an impact on communication distance as well. Like this paper has discussed about rate loss, uh, with not giving too much of information exactly, but this shows that the rate loss that we have is actually related with the secret key rate that we had, and this depends on the delta T and TC we pick, because the secret key rate depends on that. So this paper demonstrates the expected key rate expected secret key rate as a function of the channel loss. So it shows that by applying temporal filtering, we can increase the tolerable loss in inside the quantum channel. And since we increase the tolerable loss, this means that we can extend the maximum communication distance. So below, you can see there is a rate loss diagram that shows how temporal filtering actually affects tolerable loss and secure key rate. So here you can see that for different delta T and TC, we have plotted this secure key rate versus channel loss diagram. And here we see that if we don't apply any filtering, we can at most we can get a 28.3, like it's going asymptotic at 28.3. So 28.3 dB channel loss. So the distance that we'll get will be a bit lesser than when we apply aggressive this aggressive delta T, like aggressive temporal filtering will actually increase our communication distance. So as you can see, the blue line, this is the most that we achieve because here delta T is the biggest. So also we can actually go to infinity as well rather than 38B, but that is not actually physically possible because of the limitations that we have in the equipments that we have, and also the detectors that we have. So theoretically it can go to there as well, but experimentally in our setup we'll try to achieve something around here, and this will mean that we will have a communication distance of like 120 kilometer or 240 kilometer depending upon the parameters that we set in our equation. So it's quite impressive, like some of the experiments have been performed which have shown something around that, like the some communication distance which is comparable to what we are saying here by extrapolating the data that we have. So overall, we see that on doing temporal filtering, what are we benefiting at? What is the impact of a temporal filtering on our any quantum key distribution protocol? So the summary is that by applying temporal filtering, we can actually reduce QBER because the dark counts reduce. We can enhance the signal to noise ratio because it will remove the dark counts and hence noise related events. Hence, there will be a clearer signal as compared to noise. But there is a trade-off between two, as we have discussed earlier. Also, we have seen that it increases the tolerable loss. So this means that the communication channel can be larger as well. Like it extends the communication distance for a secure key distribution. This also optimizes the shifted key fraction, like uh, shifted key, not just shifted key fraction, it should be secure key rate as well. So it improves how many bits that can send per pulse to place by per pulse to from Alice to Bob. You can maximize this as well by temporal filtering. Okay, and because this also happens via preserving the valid photon events as and filtering out the noise. So also as we saw, it improves G20 as well. So this makes our system, this improves anti-bunching and hence enhances the photon purity of our system and enhances the system security. So this was all that we expect that the author have not we accept that the author has covered in his paper, like what he expects the impact of temporal filtering will be on the different parameters for a good quantum protocol. So there will be many practical implications of this because quantum cryptography will help us in long distance communication and uh, secure communication as well. So that was it from my side. Thanks everyone. After this, Rashmi will continue.
Hello, my name is Rashmi Meena, and I will gonna proceed from the means I will gonna explain the subpart of the performance optimization via temporal fitting, that is real-time photon status monitoring in QKD, and then I will proceed the explanation of the simulation. So let's dive into the first part, real-time photon statistic, and how it will help us to optimize this process. So as we know that um, in real, by analyzing the photon statistics of the single photon source SBS in real time during quantum key distribution, we can we can ensure security and detect potential attacks. And the key metric used is the G20, means second order autocorrelation function, which quantifies the probability of multi-photon emission event. So if G2 zero value is close to zero, it indicates exactly indicates the high single photon purity. And if G2 zero value is means not equal to zero or some greater than 0.5, so we will say that there is unwanted multiphoton. So this is the basic concept. And then if I ask that why we are monitoring G2 zero in real life, so the main simple reason is for this is like in QKD, we know that Eve can exploit multi-photon pulse to gain partial key information via photon number splitting attack. So photon number splitting attack is just um, we are close enough to make a single photon source, but there may possibility to come like uh, they may possibility to photon come in bunches. So if there is two photon coming and if at that time if interrupt that, so if what happened that if can take information from by photon number splitting, if can get the information of that signal. So this is called PNS attack. And to ensure that this happens or not, we monitor the G2 value. So real-time monitoring ensure that the photon statics remains supposonian and detect anomalies like if I get unexpected increase in G2 zero graph, then this is directly indicate that the attack happened. So what should be the without attack G2 zero G2 tau graph looks like? Is like at zero, it means at zero is equals to tau is equals to zero. There is no multiphoton, then there is zero, then after a certain interval, there is a peak happen. So this plot is just explanation of that. And now I proceed into how we monitor the G2 in real time, how we measure, monitor the G2 zero. So for this, the method is like first concept of photon detector event. What is that? Is like in Bob side means receiver side. He records the timestamp of photon detection across all four polarization. What the four polarization is like horizontal, vertical, diagonalized, and anti-diagonalized. So each detection event is logged with a high precision. Yeah, okay. So this type of graph we getting this type of graph for all four polarization of time difference in tau between all possible pair of detection event is constructed. So this is called the G2 tau histogram. And the key reason in the histogram is like zero delay peak means tau is equals to zero. Represent a coincidence where two photon arrive at the same time. Tau is equals to zero means two photon arrive at the same time. It's obviously should be zero if we are constructing SPS. So from graph we can see that there's very less value of G2 tau means this is just a noise means we have good SPS, single photon source. So uh, let's proceed further. And the side peak, this is the side peak around zero, tau equals to zero. The side peak tau does not equal to zero, represent uncorrelated photon detection. That is from dark count or re-excitation of the quantum matter. So these peaks are from the dark counts and re-excitation. So the formula that this given in the paper is like the coincidence at tau equals to zero and divided by the average coincidence at tau does not equal to zero. This formula can be reduced into NC equal to zero divided by N side. What is the N or N side? NC equals to zero means count in zero. Delay peak means how many count we are getting at tau equals to zero, and N side is just the average count in side peaks. The average count in side peaks. So if we divide it, we can the G2 zero and we can monitor and we can tell like if I further interpreting the value of G2, like if the G2 zero equal to zero, then we can say that there is no multiphoton emission. perfectly single photon source, and if it is less than 0.5, this is good signal photon source, like suppose what we are in our case. And if the G20 is equal to 1, means a coherent laser, Bosonian statics, and G20 is greater than 1 is classically light. So this is the basic concept how we measure G20, why is important. So now let's go one more further step, like why this matter for QKD, quantum key distribution. If G20 is too high, means multi-photon pulse exists, which could be exploited in photon number splitting attack. By monitoring G20 in real time, the system can detect security branches. Okay, so this is why it is important in QKD, as I already mentioned about. So let's go further and talk about the finite key effect and accumulation time. So what is finite key effect? It's just a like in QKD, finite in means at, when we are explaining BB84, or in that case we are assuming that the key length is infinite, but in real life implementation cannot collect the infinite number of photons. Okay, so this is the finite key effect. And also, what is the accumulation time? Accumulation time is how long the data is collected before processing, is called the accumulation time. So the effect of both um, affect the security and key generation rate. So let's discuss about how it affect. So accumulation time trade-off. Let's discuss about this. So um, this plot we are gonna use this here. So short accumulation time means we are measuring data for short accumulation time before processing. So if let's say there's accumulation time is 10 seconds, so we get the key faster, very fast, because the accumulation time is very less. So if the because of this, there's a very large uncertainty of GT, as we can see from this graph. Like for integration time, means accumulation time is very less, means 10 seconds. The error means uncertainty in G20 is very high, the lighted blue part. So and the paper gives the exact value, like plus minus 43%. And this make security analysis unreliable. Okay, so now let's do the long accumulation time. Let's say 360 seconds, means around 100 order, means here. So this we can see that G20 uncertainty is less compared to this, means plus minus 6% error. So we can say this stronger security. Here is the we are in the strongest security region. So slower key rate. That's why there's a slower key rate, because the time has increased, and lower decay because key distillation. And so because by looking this plot, and we can optimize the block size, and we can say the what is the means optimal value of integration time at block size, so that G20 value is uh, okay for, means uncertainty in G20 value is such that we can use it as a SPS, and we can further perform our QKT experiment. So the optimal block size, we in the paper mentioned that 1.47 megabit shift with error 16%, and suitable for finite key analysis. And for 60-second block, uh, approximately 8.93 megabit, the error is 6%. That will goes into near asymptotic security. Okay. Okay. So this is the final. This is the optimal plot, means for 60 and 60. 60 and 60 is the optimal range for time for G20 value. So now let's. This is how we this is in this section I explain why real-time photon statistics is important to optimize the G20 value, means optimize the QKD process. So there's another thing like simulation methodology for optimizing the QKD performance via temporal filtering. So now let's go further. So the simulation um, uh, aim to evolve how temporal filtering is like for how many time we are measuring the photon means there is a window like in the bob side. So we are not collecting photon in whole time range. We are open the detector only for the that time at which we are expecting to photon come. So that is the temporal time filtering simply already mentioned or explained by other members. So the time filtering of the single photon pulse would enhance the QKD performance. Yes. So under varying experimental conditions. So we are let's dive into the what kind of various condition. By modeling different combination of pulse lifetime and noise level. The study identify optimal filtering strategies to maximize the secret key rate. So in the paper, they are using two parameters for this. First is lifetime and second is noise level. To so low noise, low noise. We have two case for noise, low and high, and two case of lifetime, low, large and small. So like first, this plot is for low noise and long pulse, and second plot is for high noise short pulse, and C is for low noise long pulse, and D is high noise long pulse. So what is this, and let's discuss all. So the simulation result, as mentioned this diagram, this is the two-dimensional heat map. Two-dimensional heat map. What is like y-axis is delta T window, and axis is TC. Uh, TC is the mid part of the delta T, means window, and the color bar is represent the S. S is the secured key fraction. So let's go further. So heat map and reveal how the secret key fraction varies with different temporal filtering. Yeah, we can see from here. For system with low noise and short pulse, low noise and short pulse, like first one, duration. The optimal filtering strategy involves you using a narrow time window. So means very less time interval, we get the optimal value, and about 1 nanosecond on the pulse peak, yielding a modest but consisting 2.5 improvement in the secret key rate. In contrast, system operating a high noise level showed that dramatic greater benefit of the temporal filtering, as you can see from the graph. The high noise short per scenario demonstrate a remarkable 184.5% improvement in secret key rate when using a asymmetric narrow filter window position slightly after the pulse peak. This configuration effectively excluded noise dominated portion of the signal while perceiving most of the genuine signal photon events. So if the noise is very less, yeah. So like in the first, noise is very less and long pulse. So we get the optimal value of delta t is for very small time delta t because is no matter depend on the whether we are taking large window or small, because the noise no matter affect the signal more because the noise level is small. That's why we are getting this is as an optimal value. So yeah, so let's go further. The simulation with a longer pulse means uh, decay with slower rate and lower pulse duration reveal the different optimization pattern. Yeah. So for low noise system with a long pulse, moderately wide filter like 2 nanosecond and center of the pulse peak provided optimal result, improving the secret key by 6%. These all data exactly taken from the paper. So this is just the numbers that I get from the paper. The most challenging scenario, high noise combined with long pulse, but because it's require an extremely narrow filter window of just about very few nanosecond and position slightly the uh, before the pulse peak, and it achieved the improvement of 148.3 approximately percent. So this is how these all for plot is help us to optimize the delta t for the our QKD. So this research overall, so this research demonstrated how careful controlling photon detection timing can optimize quantum communication performance. So the optimal temporal filtering strategy depend on two key filters: environmental noise level and photon preservation. It may depend on all, but in this paper is mainly in simulation part. They took these two parameter, and this is what the explanation. And this is my part. Thank you.
Hello everyone, my name is Manish Vashni, and as Rashmi just mentioned that for finding the ideal secret key rate, we have done some simulations. So going through all individual lines, I don't think it would be a feasible idea. So what I've done is I have made a small flowchart to explain the whole code. So the convention is to read this flowchart, the yellow the yellow rectangles means it's a class, and the white rectangle means it's a function. Okay, and the gray rectangle means how that particular function works. So I have a class which is named QKD optimizer, and as you can see, it has three functions and obviously one constructor. So the moment I made a object of this class means this generates pulse shape would be called. Okay. After this function is called, it will make an exponential graph, and it will make a Gaussian graph, and will mix it. In coding language, we say it with uh, np dot convolve. Hello everyone, my name is Manish Vashne, and as Rashmi just mentioned that for finding the ideal secret key rate, we have done some simulations. Okay, so as you can see, going through individual line of code, I don't think it would be a feasible idea. So what I've done is I have made a small flowchart of which function is calling which function, just to see the flow of the code. So the basic convention is uh, class. The yellow rectangle is a class. All the white rectangles are functions, and all the gray rectangles means how that particular function is working. So the moment I made a object of this class QKD optimizer, obviously that constructor will be called. Okay, the moment constructor is calling, inside the constructor we have generate pulse shape. Okay, how I made a pulse shape? I have made an exponential graph, I have made a Gaussian graph, and I have mixed them together to get the required shape of pulse. Okay, and also these white rectangles are in chronology. So first the constructor is called, and I have made a pulse. Okay, then this plot pulse and filter function will be called. Okay, this function will be called, and then it will plot that particular pulse and highlight that part of the pulse which is inside the temporal filter window. So what I mean is that particular function will make this graph. So this growing graph is an exponential. So sorry, this growing graph is a Gaussian, and this is exponentially decay. And I've mixed them together to make the required pulse. And this red thing is made from that second part, highlighting only that part which is inside the temporal window. Okay. After that, this function would be called, this is plot 2D secret key rate. Basically, for each TC and for each delta T, I will find secret key rate S. ठीक है. So first we will initialize the grid. Okay. And then for each GT, for each TC, we will find, so basically for each pixel, we will find secret key rate. Okay. The moment this function is called, for finding the S value for each pixel, this function will be called secret key rate. Okay. And this function will use the formula for S. It is given in the paper. When this function is called, inside this function, apply temporal filter is called. What this function will do, it will define the bound. For example, let's say delta t value is 1 second. So 0.5 second on the left and 0.5 on the right. This function, we will define the bound. Okay. And then we will extract only that signal which is inside that window, this inside this bound. Okay. And then we will calculate this QBER, quantum bit error ratio, and finally the FNR ratio. And this applied temporal filter will return these three values. Okay. After this function, we will so basically all this 1, 2, 3 function will plot this graph. Okay. So for each pixel, we have calculated S, and we have mapped. So basically, it's a three-dimensional graph. Okay. So for each pixel, for integrating the S value, we have used colors. So it is on the y-axis as seen in the spectrum. So higher values are bright and lower values are dark. Okay. So then in the paper, there is a simulation part in which we have made 4 graphs for different noise levels and different decay levels. So basically, we are going to make 4 graphs: low noise, long pulse, high noise, short pulse, low noise, short pulse, high noise, and long pulse. So basically, the previous graph that we have made, we have to make it 4 times for different parameters. Okay. So the issue is we are not able to get the exact graph which are in the paper. Okay. Why? I think the code is right, but somewhere in the paper, the paper has not explicitly written values of some parameters. So I was just playing around those parameters just to get exactly the those graphs which are in the paper. So I was not able to do that. So for example, there is this parameter called FE. In this paper, it has cross reference from 28th reference. I did go to that reference, and that reference also have not given the value of FE. It has just given the lower bound that FE should be greater than 1, but the exact value, no. So I've just put it F equals to 1.2 or 1.3 something. So we have to play around those values, and maybe then we can find the exact graph that are in the paper. Still, how to read this? How to read these graphs? So basically, in this whole, for a particular graph, there is just a brightest spot. So why we are doing this simulation? We have to find the optimal value of delta t and tc. What is the optimal value for which the S value is the highest? Okay. So we have to find the optimal value, and then we can finally found that particular thing that we were trying to find. So as you can see, this is not exactly the graph that we want to find. I think code is fine, but we have to play with some parameters. And believe me, there are many parameters like HE, and FE, and P click, and many more. But this is the basic idea of the code. And then we have two headings: discussion and results. So basically, they just rediscuss everything which is in the which are in the starting. For example, this is discussing the key achievements, experimental validation, security advantages, and broad. I can just read it for you if you want. So basically, key achievement is we have done temporal filtering to find and we have used SPS to find the ideal secret key rate. These are just experimental validation tested on a solid state quantum dot. So just all the specifications. It has broad applicability and the future work. I'm running out of time, and the results, and in the results cell, what we have done is for each thing, for example, the single photon source, QKD setup, what are the exact formulas, what are the exact values that are written in the paper. Results contain those. So for instance, the frequency of pulse is 80 megahertz, sorry. And we found G2 tau for, minimum to be 0.089, all the values. And then you can see we have 4 polarizations. What are the frequency? What are the dark count rates? And what are the key formulas of QBER and the secret key rate that were using in the function? And what were the optimization of values of delta T? And then the key results were QBER was found to be 0.48%, and this tolerable channel loss, that decreasing graph, was at 38 decibel. So I think that's a wrap up. I think we have covered everything. We have simulated everything. The graphs are not fine, I know. And I think that's the conclusion of the whole paper.